Hi guys, it's Daniel here, and today we're going to do problem number 4 of my USAMO mock test. So let's first read the problem. Let f be a non-decreasing function from natural numbers to natural numbers, such that f of n divides n is true for only finitely many n. Prove that there exists a constant c greater than 0 such that f of n is greater than cn for all n. So intuitively, this basically just means that fn grows faster than linear. So how might we go about solving this? Well, one idea when we have any type of problem, not just a number theory problem, but just any type of problem, is to consider the contrapositive. And by contrapositive, what I mean is that if we want to prove, oh, that's way too skinny. If we want to prove that statement A implies statement B, so in this case it's fn divides n true for only finitely many n, is statement A, and statement B is there exists a constant c greater than 0 such that fn is greater than cn for all n. If we want to prove this, then proving not B implies not A is equivalent. So these two things are equivalent to each other. And if you want to know how to prove this, well, it's not that hard. You can just logic it out yourself. So let's apply this sort of method and instead try to solve the contrapositive. So the contrapositive of this problem would be that if there does not exist, so if there does not exist any constant c greater than 0 such that fn is greater than cn for all n, then we prove that fn divides n is true for infinitely many n. So infinitely many n. So if fn greater than cn is not true for any c that we choose, then we prove that fn divides n for infinitely many n. So how might we go about doing this? Well, let's consider a function g of n. Define it as f of n, or not f of n, sorry, n minus k times f of n, where k is some integer that, let's say, greater than or equal to 1. So if we can show that g of n has a root, so g of n equals 0 for some value of n, then this implies that n equals k times f of n, which means that since k is a positive integer, that fn divides n. So now all we need to do is show that gn obtains a root. And the fact that we let k be any positive integer means that if this gn having a root is true for infinitely many of these positive integers, then we're done, because then we can find an n, infinitely many n, such that fn divides n. And we know that all the n that we find are unique because these k's are all unique. So if two of the n's that we find from different values of k are the same, well, that's not possible because of this equation. N equals k times f of n. We can't have k be two different things and have both of these corresponding equations still be true. So now we need to do is find that this is true for infinitely many k. So in order to prove this, let's try to do a sort of continuity argument. Like, if we can prove that at some point g of n is less than 0, and at another point g of n is greater than 0, and that g of n also increases by at most 1 each time, or something similar to that, then it follows that gn equals 0 at some point. So if we want to attack it like this, of course, let's first consider g1. g1 is equal to n minus k times f of 1. And note that f of 1, because the function goes from natural numbers to natural numbers, f of 1 is greater than or equal to 1. So this is less than or equal to 1 minus k. And since k is a positive integer, this is less than or equal to 0. Okay, so that's nice. We have that g of 1 is less than or equal to 0. So now all we need to do is find a g of n such that it is greater than or equal to 0. So now note that we still haven't used this condition yet, such that there does not exist a constant c greater than 0 such that f of n greater than cn for all n. So to use this, we let c equal 1 over k. So this condition tells us that there exists an n. So use this fancy symbol, which means exists. That's supposed to be a backward e. Exists an n such that, abbreviated as st, such that f of n is less than or equal to n over k. For this, we just let c equals 1 over k, and by using this fact, this is true. So what does that tell us about g of n for this particular n? Well, let's just plug it in and find out. N minus k times f of n is equal to g of n. And f of n less than or equal to n over k means that this thing is greater than or equal to n minus k times n over k equals n minus n, which is equal to 0. So this is perfectly what we're trying to find, because now we know that there exists this n such that g of n is greater than 0, and we also know that g of 1 is less than or equal to 0. So now all I need to do is prove that g increases by 1, at most 1 each time. So in order to prove this, we note that, first of all, g of n equals n minus k times f of n. This n, every time we increase n by 1, this part increases by at most 1. In addition, since fn is a non-decreasing function, this part always subtracts from g of n. It never adds to it, because each time we increase n by 1, this fn stays constant or increases also. So this part can only take away from the overall value of gn. So this proves that g of n can increase by at most 1 each time, because the only thing that contributes to gn increasing is this n term, and we know that this n term can increase by at most 1 each time. Therefore, g of n increases by at most 1 each time n increases by 1. So therefore we are done, because if we consider a graph of g, if we let g1, so if this is 1 and this graph is of gn, so if this is 1, then g of 1 is like somewhere around here, and then 2, it might be somewhere around here. 3, it might be back over here again, I don't know, 4, up here again, but all the way to that specific n where the point is up here. So since it can increase by at most 1 each time, at some point it has to hit the 0 point before going up to reach this gn point. So at this point, this is the point we're trying to find, where gn equals 0. So at this point, n equals k times f of n, or in other words, at this point, f of n divides n. And this, in fact, works for all values of k, such that it is a positive integer. So we've not only proved it's true for infinitely many n, we've proved that's true for each value of n over f of n. So, well, that solves the problem, because now since we proved the contrapositive, we have proved the original problem, so we are done.
Hey guys, Zong here, back to another math video. Today we're going to be doing Daniel's USMO problems number 3. It's one of the easier ones on the mock test, but without further ado, try to solve it yourself.